Okay, so we're going to look at different types of mean, and there's actually a formula we can use to understand lots of different types of mean, and that's this, where if you have a function f and you've got your data as x1, x2 up to xn, so you've got n data values, you apply f to each of these individually, add them up, divide by n, divide by how many there are, then at the very end take the inverse of f of this result. So we'll look at a few examples. Our first example isn't very interesting, perhaps. We've got f of x is just equal to x. So you think about what the inverse function is going to be. If this function just maps a number to itself, its inverse, we can say f inverse of y is just going to be that same number y. So if we apply this, write this all out, you'll see that we're just going to get f of x1 is just x1 and so on. So here we'd have x1 plus x2 all the way up to xn divided by n, and then when we take the inverse here, we don't need to do anything, we just leave this alone. So you can see with the function fx equals x, we actually get what we call the arithmetic mean here. So this is the most familiar one. You might just call this the mean, where you add up all your values, divide by how many there are. And this is useful in most circumstances because it gives an idea of sharing out the average amount. So if we look at another example, let's look at a different function. So if we make this more interesting, we'll have the function now fx is 1 over x, so like a reciprocal function. So let's think about what the inverse would be here. Well, if we had f inverse of y, this would actually be 1 over y. So this function is kind of the same as its inverse here, because if you have a number, you do 1 over that, and then you do 1 over the answer, you get back to your original number. So let's see what happens when we apply this to our data, x1 up to xn. So we do 1 over x1 first of all, 1 over x2, all the way up to 1 over xn. Then we've got to divide this by n, and then we have to do f inverse to all of this. So we have to do 1 over all of this. So I'll just write this as to a power of -1 to show that reciprocal. So then when we do this 1 over, this would just flip the fraction. So we're going to get now n over the sum of all of these reciprocals, so 1 over x1 up to 1 over xn. And you might recognise this as this is called the harmonic mean. So the harmonic mean is a really useful one, and just one example that we could look at for why the harmonic mean is something people are interested in is it's really useful for looking at calculating with average speeds. So let's have a look at a simple example where you go one way. Let's say you go at 4 miles per hour in one direction, but then you go back the same journey, but now at 12 miles per hour. So you might think just adding these together, 12 plus 4 gives us 6, divide by 2. You might think the average speed for this journey would be 8 miles per hour if you're applying the arithmetic mean from earlier. But it turns out that this isn't actually true. So we could understand this for example, if we put some distances on here. Let's say this distance is 12 miles. So you go 12 miles at 4 miles per hour. So this is going to take 3 hours. And then if you go back 12 miles at 12 miles per hour, this is now going to take just 1 hour. So you can see a total journey of 24 miles has taken 4 hours. So if we do 24 divided by 4, we actually should get 6 miles per hour. So this initial, using the arithmetic mean, doesn't give us the right answer, but using the harmonic mean, we'll see, is going to give us the correct answer of 6 here, because here we've only got 2 values, so here we'd have n is 2, and if we calculate 2 over, it would be 1 over 4 plus 1 over 12. So 1 over 4 plus 1 over 12 gives us a third, so we do 2 divided by a third, and you would indeed get 6 miles per hour, which is the true average speed. So you can verify this a bit more formally and more generally if you like, if you're interested too. So now let's look at another type of mean called the geometric mean. So the idea here is if you have n values, you multiply them all together, then you would take the nth root, or equivalently you'd raise this to the power of 1 over n. So just very briefly, why is this useful? Well, the geometric mean is really useful if you want to find an average multiplicative change. So this could be, for example, in 1 year, if a price doubles in the first year, but then in the second year, on top of that, it multiplies by 8, so it becomes 8 times more expensive than it was at the end of the first year. The net result here is that it's become twice as expensive times another 8, so the net result is that it's become 16 times as expensive. So if you want to talk about what was the average change per year, taking the arithmetic mean would give us 2 plus 8 divided by 2 would give us 5 times more expensive per year. But then this would be times 5 and times 5 again. This would suggest that your price was now 25 times as big at the end of the 2-year period. So the arithmetic mean doesn't really work for us there, whereas the geometric mean, if we take 2 and 8, multiply them together, get 16, and then we would square root this, because n would be 2 here, you would get 4 with the geometric mean. And this does make sense, because if something multiplies by 4, then multiplies by 4 again, we would get the 16. And also, if you're interested, the harmonic mean here would be 3.2, which wouldn't be any good either. So the geometric mean is really useful for tracking multiplicative changes like this, among other things. So how can we get the geometric mean to look like this with our function f? Because you can see here, we need to somehow have some functions being added together, whereas in the geometric mean, the formula here involves multiplication. Well, the natural way to go between addition and multiplication is actually to use logarithms. So if we try this with f of x is, let's say this is the natural logarithm of x, then we're going to take advantage of the property of logarithms, that if you have the logarithm of a product, so let's say we've got ln of a times b, we can rewrite this as ln a plus ln b. So now you could see how if we had ln x1 plus ln x2 and so on, you'd be able to turn this into the natural logarithm of a product. So just before we start calculating this, we also need the inverse function here. So if we have the inverse function of a natural logarithm, this would just be e to the power of y. So e to the power and natural logarithm cancel each other out. So now if we try and apply this to see if this gives us the geometric mean, first of all, we're going to take natural log of all of our values, add them up. So we've got ln of x1 plus ln of x2 up to ln of xn. We're going to divide all of this by n, and then we need to do e to the power of this. So we'd have e to the power of all of this fraction here. But then using our property of logarithms, we can turn this sum of logarithms back into a product. So we can now write this as e to the power of, we'll have ln of x1 times x2 times x3 up to xn, and then we've still got this factor of 1 over n. I'm just going to write this as e to the ln of this product times 1 over n rather than dividing it by n. And the reason we're doing this is you can now see this is, if you have a number raised to a power times by another number in the power, it's basically like taking this e to the ln of this product to the power of 1 over n. And then here, using the fact that e and ln are inverse functions of each other, e to that power, this cancels out and just gives us the product then, x1 times x2, so this whole product up to xn, and this is raised to the power of 1 over n. So I think this is really beautiful that we can get the geometric mean in this general format as well using logarithms. And it's really cool here, you could actually try this with a different base logarithm. It doesn't have to be the natural logarithm. And then when we take inverses, this would cancel out and you would still get the geometric mean. And it's really interesting as well for the arithmetic mean, for example. This worked before we had f of x just equal to x, but because we take the inverse function, we could actually take, for example, f of x could be any linear function, ax plus b, and then when we take the inverse, this would cancel out. If you're interested, you can have a check of that. And now finally, we're going to see something really cool happens when we take limits. So if we consider our f function to be f of x is x to the power of k, so its inverse would just be f inverse of y is y to the 1 over k. Something really cool happens when we take limits as k goes to infinity. So if we write this out, we'd be looking at the limit as k goes to infinity of, we'd have x1 to the k plus up to xn to the k, all divided by n, and then raised to the power of 1 over k. And to see what's going to happen with this, I think it's helpful just to look at a concrete example. So if we just go with a small data set, let's say as k grows to infinity, let's look at this where we've got just 2, 3 and 4 are our numbers. We've got 2 to the k plus 3 to the k plus 4 to the k. We have to divide this by how many data points we've got, so divide by 3, then raise all of this to the power of 1 over k. So you can perhaps see here, just informally, that as k gets bigger and bigger, the contribution from 4 to the power of k is going to be much, much bigger than the contribution from 2 to the k or 3 to the k. So actually, asymptotically as k goes to infinity, we can ignore these two terms, just working informally. We can say this is going to be basically the same as 4 to the k divided by 3, all raised to the 1 over k. And then you can see here the powers of k cancel with the 4, so we get 4 times, then we've got 1 over 3 to the 1 over k, so we'll write this as 3 to the negative 1 over k. So now if we've got 3 to the negative 1 over k, as k gets bigger and bigger, this is going to be getting closer and closer to 3 to the 0. So 3 to the 0 is just 1, so as k goes to infinity then, we can say informally that this is going to give us 4. So you can see here 4 was our biggest number there, and you could see how this could generalise that as long as we're working with positive numbers here, we're going to get our biggest contribution is always going to be the maximum value here. So we've not really shown that very rigorously, but you can say that the limit as k goes to infinity is going to be the maximum of our data set. And something really interesting is going to happen as well if we take limits as k goes to negative infinity. So we'll just rewrite this out, but we'll go with, rather than taking limits to negative infinity, if we write f of x is now x to the power of negative k, or 1 over x to the power of k, then the inverse would be f inverse of y would be y to the negative 1 over k. So we can look at another similar example with the same data set here. So we can say that as k grows to infinity here, so taking limits and then it's going to be x to the negative infinity effectively, we would have 2 to the k would become 1 over 2 to the k, and then we'd have 1 over 3 to the k, and we'd also have 1 over 4 to the k. Then we divide this by 3, and then we would have to raise this to the power of negative 1 over k when we do the inverse of f here. So this is all to the negative 1 over k. But you can see as k gets bigger and bigger here, our contribution from the 1 over 2 to the k is now going to be our biggest contribution, whereas the contribution 1 over 4 to the k is going to be so much smaller than the other two that we can ignore that, and similarly we can ignore the 1 over 3 to the k compared to the 1 over 2 to the k. So we would just be left with, this is going to be equivalent then to having 1 over 2 to the k all divided by 3 and then raised to the power of negative 1 over k, just working quite informally there. So then you can think of this is basically 2 to the negative k raised to the negative 1 over k. So just like before, this is going to cancel and give us 2 times, and then we've got 1 over 3 to the power of negative 1 over k. So the negative power turns this from a 1 over 3 into a 3 to the power of 1 over k. And then as k goes to infinity, we're going to have effectively, this is going to get closer and closer to 3 to the 0. So just like before, that's going to grow to 1. So you'd have 2 times 1, which would go to 2. So you can see now, taking limits as k gets smaller and smaller, or having the reciprocal, we've ended up with the minimum value. So we can say, again quite informally then, that the minimum of a data set, x1 up to xn, can be found as the limit as k goes to infinity of, we'd have 1 over x1 to the power of k plus 1 over x2 to the power of k, and so on up to 1 over xn to the power of k. And we'd have to divide all of this by n and then raise this to the power of negative 1 over k. So we've got the minimum and the maximum then, but we shouldn't really think of these as means because we haven't expressed them using this formula with a function f, but we can think of them as being limits of means. And you might be wondering what happens if there's more than one value in our list that's the maximum here. So if we had, instead of 2, 3 and 4, if we had 2, 4 and 4 for example, would this function still work? So you would just end up with, instead of here where we say that the 4 to the k term dominates, you would have 2 lots of 4 to the k here, and that 2 would be raised to the power of 1 over k. So we just have our previous answer there, but we'd also need to multiply by 2 to the power of 1 over k. Unfortunately here, 2 to the 1 over k still goes to 1 as k goes to infinity. It's still like having 2 to the 0. And this would work as long as we have a fixed number. So you could actually have any number of items in your list could be equal to the maximum, and if there were m, you'd end up with a multiple of m in there, so a factor of m, which gets raised to the power of 1 over k. But then this would still go to 1 as long as m is fixed as k goes to infinity. And similarly for the minimum, you would end up with a factor of m here, and this would be raised to the negative 1 over k, but m to the negative 1 over k, this would still be like having m to the 0 as k goes to infinity, so this would still go to 1, and this would still indeed give you the minimum or the maximum then, even if there's more than one value equal to the minimum or the maximum in either case. So a final thing to think about then might be what happens if we take limits not as k goes to infinity or negative infinity, but actually as k goes to 0, as something to think about then.